Hello, welcome to Alpha Beta Tutorials. Today we are diving into a fascinating topic that combines mechanics and structural engineering, the cantilever and depression experiment. But before we dive into the practical demonstration, let's take a moment and grasp the basics. What exactly is a cantilever? In simple terms, a cantilever is a structural element that projects horizontally into space, supported only at one end. It's a common sight in architecture, engineering, and everyday objects. When a load is applied to the free end of the cantilever, it experiences a downward deflection known as depression. Without further ado, let's jump into the world of physics and uncover the secrets of cantilever depression together. You are provided with a G clamp, a meter rule, a half meter rule, a retort stand with clamp, weight hanger, slotted masses, sellotape, a pointer, and a piece of thread. Clamp the meter rule firmly to the bench such that 80 centimeters of it projects outwards throughout the experiment. So we have 80 centimeters of the meter rule projecting outwards and clamped at this end. We are going to use this diagram as a guide to perform the experiment. Attach the pointer and weight hanger securely at the free end of the meter rule by means of a sellotape. So we make a loop of string to hold the weight hanger. And we attach the pointer. So we attach the weight hanger to the loop of string, and this is the pointer. Use the retort stand to clamp the half meter rule vertically and place it such that the pointer moves freely over its graduation. Record the initial pointer position H1 on the half meter rule. So without the weight hanger, we record the initial pointer position. So we have 27.4 centimeters. Place a mass M is equal to 50 grams on the weight hanger and record a new pointer position H2. The weight hanger alone is 25 grams, so we add another 25 grams, making 50 grams. And we record the new pointer position H2, that is 28.6 centimeters. And we are going to evaluate D, which is equal to H2 minus H1, and then evaluate log D and log M. So we have D1 representing the first trial of the experiment, and is H2 minus H1, so we have 28.6 centimeters minus 27.4 centimeters, which gives 1.2 centimeters. But we want to leave D in SI units. The SI unit of length is meters, so we divide 1.2 by 100, and it's 0.012 meters. So we hung a mass of 50 grams, which is 0.050 kilograms. We want to leave mass in SI units. That is 50 divided by 1000. And D1 is 0.012 meters. And we are going to repeat the experiment for 4 other values of M is equal to 100 grams, 150 grams, 200 grams, and 250 grams. For each case, we will record H2 and evaluate D, log D, and log M. So we change the mass to 100 grams, that is 0.100 kilograms. And the new pointer position is 29.9 centimeters. We subtract 27.4 and divide by 100 to change it to meters, and we have 0.025 meters. We change the mass to 150 grams, that is 0.150 kilograms, and we have a pointer position of 31.1 centimeters. We subtract 27.4 and divide by 100. We have 0.037 meters. We change the mass to 200 grams. And the pointer position is 32.4 centimeters. We subtract 27.4 and change it to meters. We have 0.050 meters. And we change the mass to 250 grams, which is 0.250 kilograms. And the pointer position is 33.7 centimeters. We subtract 27.4 centimeters and change it to meters. we have 0.063 meters. So we are going to repeat the experiment and find the mean of D1 and D2. So the initial pointer position is 27.4 centimeters. We hang a mass of 50 grams and we have 28.6 centimeters. We subtract 27.4, convert it to meters. We have 0.012 meters. We change the mass to 100 grams and we have 29.8 centimeters. We subtract 27.4, convert it to meters, we have 0.024 meters. We change the mass to 150 grams and we have 31.1 centimeters. We subtract 27.4, change it to meters, we have 0.037. We change the mass to 200 grams and we have 32.4 centimeters. We subtract 27.4, change it to meters, we have 0.050. And finally, we change the mass to 250 grams. And the pointer position H2 is 33.7 centimeters. We subtract 27.4 centimeters and divide the result by 100 to change it to meters, and we have 0.063 meters. So we have the mass in kilograms, D1 in meters, D2 in meters, and we find the mean D also in meters, that is D1 plus D2 divided by 2. So 0.012 plus 0.012 divided by 2 is still 0.012, and 0.025 plus 0.024 divided by 2 is 0.025 to 3 decimal places. The average of these two values is 0.037, this one is 0.050, and this is 0.063. And remember, the question says we should evaluate log D and log M. So we have log D here and log M. Remember, log D has no unit and log M has no unit. So for log D, we take log of the mean D. So log 0.012 is negative 1.92. We leave it in 2 decimal places. Log 0.025 is negative 1.60. Log 0.037 is negative 1.43. That of 0.050 is negative 1.30, and log 0.063 is negative 1.20. And for log M, for the first value, we take log of 0.050 and it's negative 1.30. That of this one is this, that of this is that, and that of this is this, and log of 0.250 is negative 0.60. So we tabulate the results. Now plot a graph with log D on the vertical axis and log M on the horizontal axis. So we need the values of log D. So for the values of log D, we convert it to standard form for easy plotting by moving this point 1, 2 and recording this value as negative 192 times 10 exponent negative 2. So we have log d slash 10 exponent negative 2, meaning the value here, when we multiply by 10 exponent negative 2, we will get this value. So the next value is going to be negative 160. The next one is negative 143, negative 130, and negative 120. For the values of log m2, we move the points 1, 2, and the first value becomes negative 130 times 10 exponent negative 2. So the next one will be negative 100, negative 83, negative 70, and negative 60. So we plot these values on the graph. So we draw the vertical and horizontal axis. Remember that all the values are negative. So we are going to use the negative axis. Both the vertical and horizontal axis are all negative. We are plotting log D on the vertical axis and log M on the horizontal axis. So we choose a scale. We will choose a scale of 2 centimeters is to 20 times 10 exponent negative 2 on log D axis, and 2 centimeters is to 20 times 10 exponent negative 2 on log M axis. So we start from 0, neg 20, negative 40, negative 60, negative 80, negative 100, negative 120, and so on. And on log M axis too, we start from 0, neg 20, neg 40, negative 60, negative 80. Each big box is 20, and so 20 divided by 10 is 2. So each small box is going to be 2. And this should guide us to plot the graph. For the first value on log D, we have negative 192, and log M, we have negative 130. So negative 130 will be between negative 120 and negative 140. And negative 192, that will be between negative 180 and negative 200. We have negative 190. So we'll move one more box and they will meet here. The next one, negative 160 on log D, is here, and negative 100 is also here. So they will meet here. The next one, negative 143. So this is negative 140. One box will be negative 142. So in the middle of the next box will be negative 143. And 83, this is 80. One box will make it 82. And in the middle of the next box will be 83. They will meet here. And the next one, negative 130 on the vertical axis. That will be between negative 120 and negative 140. And negative 70 will be between negative 60 and negative 80, and they will meet here. The next one, negative 120 on log D axis is here, and negative 60 is also here, and they will meet at this point. So we draw the line of best fit. Calculate the slope S of the graph. So we draw this horizontal and vertical lines and label it A here, B and C. The slope is changing BC over changing AB. And for changing BC, we have negative 98 minus negative 200 times 10 exponent negative 2. And for changing AB, we have negative 40 minus, this is negative 138 times 10 exponent negative 2. So times 10 exponent negative 2 can cancel out, and negative 98 minus negative 200 is 102. Negative 40 minus negative 138 is 98. And when we divide 102 by 98, we have 1.04, and that is the slope. From the graph, determine the pointer position H0 corresponding to the mass M0 is equal to 120 grams. So first of all, let's convert the mass to kilograms. That is what we plotted. We plotted the mass in kilograms. So we divide 120 by 1000 and we have 0.12 kilograms. And let's find log m. That will be log 0.12, which gives negative 0.92. And let's change it to standard form by moving this point 1, 2. So we have negative 92 times 10 exponent negative 2. From the graph, when log m is negative 92 times 10 exponent negative 2, on log m axis, negative 90 will be between negative 80 and negative 100. So we move one more box and draw this straight line to meet the line of best fit, and we project it to log d axis, and we have negative 152 times 10 exponent negative 2, and negative 152 times 10 exponent negative 2 is negative 1.52. Remember, log d has no units, and when we find antilog of negative 1.52, we have 0.030 meters. Remember, the unit of d is meters. But we know d is h2 minus h1. And in this case, we replace h2 with h0. And we know d to be 0.030 meters. And h1 is 27.4 centimeters. But since d is in meters, we change h1 to meters. And we bring this to the other side to add. And so h0 is 0.304 meters. If we want the answer in centimeters, we multiply this value by 100 and we have 30.4 centimeters. It means when we attach a mass of 120 grams, the new pointer position will be 30.4 centimeters.